Today's video is about why is the surface area of a sphere what it is. And here's all the explanation that I am gonna do later in the video. And right now I'm gonna tell you the reason why I study this part of the math. Why I was interested in this. Well, the reason was because I was at school listening to the math class, and my teacher said that the surface area of the sphere is 4 pi r squared, and also the volume of a sphere is 4 divided by 3 pi r cubed. So and then I thought, why are those what they are? So I asked the teacher, but it didn't come into me for much help. So I looked it up after a few months, and I got some good answers. So I got to study about this, and now I'm making into a video. Hello, and my name is Teddy Kim, and today we are gonna talk about the surface area of a sphere. Now, this is about the derivation of the surface area of the sphere. And now, the first thing what you need to know is, what is pi? I mean, if you're asking why the surface area of a sphere is 4 pi r squared, you should know pi. As I wrote here, the answer to the surface area of a sphere is this formula. Anyways, and this formula is what we are gonna get after some derivations, after some things that I'm gonna talk about. Now pi is the circumference divided by diameter. I think I spelt it wrong. Now, pi is circumference over diameter. This is the definition of pi. And so basically, if there's a circle, this thingy is the circumference, and the line that's dividing it is the diameter. Basically, you can think it as like that. Now we're gonna define what is a circumference. So we multiply diameter to, I just write dia. Actually, there's a better way. Because, and if there's a circle, and here's the center of the circle, this is a radius, and that makes a diameter 2 times the radius. So basically, if you want to get rid of the diameter, we can multiply 2r. 2 multiplied by r multiplied by pi. So that would make, we're multiplying that to here too, so we can keep that equal sign. So multiply it by r times 2. Basically the same thing, so we can just not think about that. So that makes 2 pi r equal circumference, which is often written L. Well, sometimes we're gonna talk it as L in this video. So 2 pi r equals the circumference. Now what we are going to talk about is the now we can get into the derivation of 4 pi r squared. Now we have a sphere here, and what we're gonna do to the sphere is draw a lot of lots of squares on it. We have a bunch of squares on this sphere. Now what we're gonna do is draw a cylinder right outside of the sphere, and it's touching the sphere. If the sphere is like this, the cylinder is like this. It's touching right to it, and also the cylinder has the same height as a sphere. So the cylinder would be like over there and like that. Now, as you can see, I drew a cylinder here, and now what we're gonna imagine is there's a stick of light, a stick that is a light source, and we're gonna project these squares onto the cylinder, but we are not gonna think about the circle sides of this cylinder. We are only gonna think about the label. The label is basically the sideways side, the side part of the cylinder, not the top and bottom part. So if we do that, we are gonna get a a lot of squares on the cylinder, and I'm not gonna draw that because why should I? It's a job that takes a long time. Anyways, I'm not gonna draw that, and if this and the square will squish and change the shape a little bit, but it won't change. But if it doesn't change the area of the square, and we put the label we make the label into a, we basically cut the label and open it, then we would get a big rectangle, and we would get a big rectangle, and the height would be 2r, because it's the height of the sphere, and the side part of it would be the L, the circumference, because it's wrapping around the sphere, so it should be 2 pi r, yes, not squared, 2 pi r. And so the area of this rectangle should be the surface area of the sphere. But keep in mind, we are putting a we can only get this right if the size of the square is perfectly is perfectly the same when you move it to the cylinder, the label. And if it is, the surface area of the sphere should be this multiplied by this, so therefore 4, that's pi. 4 pi r squared. But why should the square be the same size when you have moved it to the label? So now what we are gonna do is derive that. Now what we are gonna think about is only a little, very tiny part of that sphere we're talking about. And I am only going to talk about one square on that sphere. So there's a sphere, and let's say that we sliced the sphere so we can see it more better. So I am only going to draw a part of it. Here is the circle, and wait. Here is the center of the sphere and the circle, and here is the label. And where the square is over here. And to get a correct calculation, the squares on the sphere has to be really small. So small that it's almost not even there, but it is there, so we can calculate. This sphere, so basically, if we have a line parallel to the label, the length of the line to the square, we are gonna call it D. And the center to the label, that length is, because this is a center, and from the center reaching out to the surface of the sphere, or the circumference of the sphere, and circumference of the circle is r. That's the radius. So this is r naturally. Radius. R means radius. Now, what we are looking at here is, in this, I said the squares squish and change their shapes a little bit when they get moved into the label. Because if you think of it, this is and wait a second. If you think of it, if there's a light source thingy here, and it's reaching out like that, and there's a little thingy here blocking it, then this thingy's length would be increased. So it would be longer. So one part of the square would be stretched outwards, but because it's a sphere, some squares should be looking a bit like this, and that would make it, if there's a if it projects onto the label, the length would be shortened. This length became this length, which is quite more shorter. So another part gets stretched inwards. One gets stretched out, one gets squished in. So what we are looking at now is how much of the squishing and stretching happens. And if you call this D and Y, we are and if you look from upwards, it would look something like this. Here's the label, and here's the square, and this length is D, and this length is R. But we are going to draw but there is going to be a sort of triangle thing if we connect it like that, sort of triangle thingy. When this gets moved on to the label, it will get stretched out. This case is this case, so it gets stretched out, and the length that stretches out becomes more and more when the D is smaller. If the D is small, the length that increases. And so basically, we can write this as an equation. The scale factor of this happening is R over D, R divided by D. So this is one part, and now the squishing part. We're now going to talk about that. Now, this is also R because this is a radius, and this is D because, well, it's on these because it's the length from the line parallel to the label to the square is still D, and because it is parallel, and this angle is 90 degrees. And we are also gonna draw a little triangle here. This angle should be 90 degrees. And also we're gonna call this angle alpha and this angle beta. Then and also, because this is a radius, or is a radius, this becomes 90 degrees. And also, we're gonna look at this. We're gonna make this look. I'm gonna draw this a bit bigger. This is 90 degrees, and this is beta. So that makes this, I'm going to show you why. The sum of the three angles in a triangle is 180 degrees. So, because this is 90 degrees, alpha plus beta should be 90. So, because this is 90 degrees, beta, this should be 90 degrees. So, beta plus alpha does it. And that makes this, beta, because it is, because this line is D, the length of the square to the parallel line to the parallel line that is touching the center of the sphere, that is parallel to the label. And also, because this is 90 degrees, this also turns into alpha. So, what can we see here? This triangle is mathematically similar to this triangle. So, when the D decreases, and if you think of the angles here, this is A, and this triangle is basically turned like that. So, this is the scaled down version of D. I'm going to call it D prime. The scaled down version of D. So if D decreases, D prime also decreases. And also, if the D increases, D prime also increases. And that means and we can, and so we can see that the scale factor of the squishing part, because this is the length of the height of the square, but this is a squished down version. When D decreases, the square's height also squishes more, we can say that this part is d over r. These are the two scale factors of the squishing and stretching. So now we multiply the scale factors so we can get how much it's so we can get if it squishes more or if it stretches more. So we multiply it, but r over d multiplied by d over r makes it, if we calculate it, this becomes 1 and this becomes also 1. So we get 1. Basically nothing. The scale factor of this tells it doesn't change. The scale factor tells us that it doesn't really change the area of those squares, even though its size doesn't change, even though it looks a bit different. So we can get now we can see that the rectangle that we get from the label, the 2r multiplied by 2 pi r, this is the surface area of the circle. And now, and as I wrote earlier, this becomes 4 pi r squared. And if you multiply that, common logic, and so that becomes this. And yeah, that's why 4 pi r squared is the surface area of a sphere. And that's all for today, this video, and bye. Oh, and also I learned this from 3 Blue 1 Brown.